The resurgence of interest in nuclear spaceships marks a significant shift in space exploration efforts, driven by both the military and NASA's renewed commitment to building demonstration hardware. This revival harkens back to the late 1960s when Phoebus 2A, the most powerful space nuclear reactor ever created, was tested at the Nevada test site. Despite its potential to transport humans to Mars, the reactor was ultimately deemed too large and costly, failing to align with President Nixon's vision that restricted space exploration to low Earth orbit. Interestingly, it was the military, not NASA, that initially sought to develop rockets with nuclear engines, aiming to use them for intercontinental ballistic missiles, ICBMs. This ambition resurfaced as the military once again recognized the strategic advantages of nuclear-powered ICBMs. The work on nuclear thermal rockets, NTRs, began with the ROVR program initiated by the US Air Force in the mid-1950s. These rockets utilized liquid hydrogen heated by a nuclear reactor core to generate thrust, significantly enhancing fuel efficiency by avoiding the need for combustion and using pure hydrogen. The challenge, however, lay in translating this concept to a flying reactor. Standard fission reactors, which rely on uranium-235 oxide fuel rods, needed significant modifications to operate at the high temperatures required for space propulsion. The early designs faced numerous hurdles, including the corrosive nature of hydrogen at high temperatures and the need for alternative control mechanisms to replace traditional control rods, which couldn't function effectively in space. The transition from theoretical designs to practical applications accelerated when NASA and the Atomic Energy Commission, AEC, took over the program in 1958, rebranding it as the Nuclear Engine for Rocket Vehicle Applications, NERVA. This collaboration led to the development and testing of several reactors, including Kiwi-A, the first of these space reactors. Despite promising initial results, issues such as hydrogen corrosion and core shedding persisted, ultimately leading to the program's cancellation in 1973 due to a shift in NASA's focus toward low Earth orbit missions. Fast forward over 4 decades, and NASA once again considered nuclear propulsion for its Mars exploration plans, recognizing that nuclear reactors could significantly reduce transit times and radiation exposure for astronauts. A small-scale NTR research program was initiated in 2017, followed by increased funding from Congress in 2019. However, progress remained slow until the Defense Advanced Research Projects Agency, DARPA, expressed a renewed interest in developing a nuclear rocket for national security purposes in 2020. DARPA's involvement brought a sense of urgency and practicality to the project, leading to the demonstration rocket for Agile Cislunar Operations, DRACO. This joint project between DARPA and NASA aims to build and test a nuclear-powered spacecraft capable of rapid maneuvers in cislunar space. Lockheed Martin, in collaboration with BWXT Technologies, was contracted to develop DRACO, which will use high-assay low-enriched uranium, HALEU, as fuel to address safety and regulatory concerns. Building DRACO involves overcoming numerous technical challenges, from ensuring the reactor can withstand the high temperatures and corrosive hydrogen environment to designing a spacecraft that can safely house and operate the reactor. The design leverages lessons learned from the NERVA program, incorporating modern materials and engineering solutions to enhance performance and safety. Upon reaching orbit, DRACO will undergo a series of gradual power-ups to test the reactor's functionality, with the ultimate goal of achieving a specific impulse high enough to support human missions to Mars. This cautious approach reflects the complexity and risks associated with nuclear propulsion, emphasizing the need for thorough testing and validation. Beyond DRACO, the vision for nuclear propulsion includes applications such as space tugs capable of ferrying payloads between Earth, the Moon, and Mars. These tugs would rely on the longevity of nuclear reactors and the availability of lunar resources, such as water, to refuel and extend their operational lifespan. Innovative concepts like bimodal propulsion systems, which combine nuclear thermal and electric propulsion, offer the potential for even greater efficiency and speed in space travel. While the development of nuclear spaceships is driven by both national security and scientific exploration goals, the broader implications for space travel are profound. The ability to move quickly and efficiently through space could revolutionize our approach to space missions, making deep space exploration more feasible and sustainable. As we continue to explore and develop nuclear propulsion technologies, the challenges and opportunities they present will shape the future of space exploration. The journey toward practical and reliable nuclear-powered spacecraft is a complex and ambitious endeavor, but it holds the promise of unlocking new frontiers and possibilities for humanity's presence in space. If you enjoyed this video, please remember to like, comment and subscribe. Until next time, thanks for watching.